so much. Yes, I'm an assistant professor in the Department of Pediatrics at Northwestern University, and I also co-direct the Fertility and Hormone Preservation and Restoration Program at Lurie Children's Hospital. And so I'm going to be talking about engineering a bioprosthetic ovary. This is all kind of bench basic research at the start, but I think from the talks earlier today on a lot of the clinical focus, a lot of animal work went into those procedures prior to translating those into the clinic. So I'm excited to describe some earlier things for you here. And so I wanted to kind of focus and start with our motivation for the research that I do. And it's really because there's several professional societies that recommend talks, discussions about fertility preservation and how hormone levels from gonads, testes, and ovaries may be affected by gonadotoxic treatments, and this is mostly for cancer patients, but it also expands beyond that. And so the American Academy of Pediatrics also recommends these types of guidelines in addition to ASRM. And the reason why these guidelines were established is because they really heard from the patients that this is one of their primary concerns. So once they've survived their either childhood cancer or young adult cancer, those who are childless still want to be a biological parent in the future. Cancer survivors describe PTSD symptoms related to infertility as long as 10 years post-treatment. And parents want fertility preservation options presented regardless of their child's infertility risk or prognosis. And this is some research that's done at Lurie Children's Hospital from a variety of patients parents that come in. They want to hear about how this might affect their child's fertility in future. And so there's been an increase of childhood cancer survivors over the last several decades, and with that, there has been an increase in understanding and an acknowledgement that there are possible fertility preservation options for them. Because we know that childhood cancer survivors are significantly more likely to be infertile or have difficulty getting pregnant than their siblings. And like I had mentioned, there's also some genetic causes for gonadal dysfunction, either because of their disease or treatment. And I just mentioned a few here, of which we have some protocols. If we can catch that early before all of their germ cells are depleted, even in those that are traditionally thought to not have germ cells within their ovaries or dysgenic gonads. For example, in Turner syndrome, we were able to find some germ cells that do exist and might be available for cryopreservation and future fertility. And so I want to describe a little bit or refresh everyone's mind about folliculogenesis, because I think we spend a lot of time down here with the either with the cumulus oocyte complex that comes out of a pre-ovulatory follicle or the fertilizable M2 egg that is released. But I want to remind everyone that this doesn't happen until we undergo puberty. And so the pediatric population that I work with don't have these mature gametes to bank in the traditional way that we use assisted reproductive technologies. However, we know that even postmenopausal women have primordial follicles still within their tissue, even if it's at low levels. But all women of all ages have at least a few primordial follicles, and this is really the start of the process. This is the bank of oocytes that are potential egg cells that could be used in the future for fertility. I also want to point out that this oocyte is surrounded by their nurse cells that together create this cell aggregate, this three-dimensional spheroid that is extremely important for each other. So the oocyte grows as it is nurtured through those granulosa cells, but those cells also produce the hormones in response to the pituitary and release estradiol and progesterone, AMH and inhibin, so those essential hormones in the ovary. And so what we do to preserve fertility in pediatric patients that cannot undergo the traditional ovarian stimulation and egg harvest is we perform a unilateral oophorectomy. And we do this because there's decades of animal research that shows that when you remove one whole ovary, the other ovary compensates and maintains the same level of hormones. This was corroborated by a large study in Norway that identified women that had unilateral oophorectomies for different indications other than cancer, and there was little difference in their age at menopause. It was about a year to 1.2 years. We also know that the remaining ovary can release more eggs if they are then stimulated for assisted reproductive technologies. And so we know that this is a safe method. And we combine these laparoscopic oophorectomy surgeries when they're already going under an anesthesia for their primary diagnosis. For example, in pediatric patients, we have to put in ports so that they can receive their chemotherapies, and so they're not getting any additional anesthesia when we do these procedures. We do it at the same time if they qualify and if they want to do this. And so we remove one ovary. This is a picture from my co-director of our program, Erin Rowell, who's a pediatric surgeon. And we process this tissue and into strips, and so we save that cortical region with the primordial bank of follicles and cryopreserve that for future use. And then again, we do this because the way that we would restore function is through autotransplantation. And one of the major physicians that does this, Sherm Silver, is in the audience. So he could take this tissue that is cryopreserved and then warmed and transplanted back. And there's been over 130 reported live births from this type of technique, and so you can transplant it either on the other remaining ovary or somewhere else in the body, and it functions. There's been reported 20 to 30% have restored fertility, and the average age of those are ovarian tissue cryopreservation that occurred at 30 years old and restored at an average of 34 years old. 62% of those were achieved spontaneously, and there's hormone production for up to 12 years, with an average about 2 to 5 years per transplant. However, in some of our patients, we know that there's a possibility of reintroducing these cancer cells, because it's ideal to take this tissue out prior to any gonadotoxic treatment, or at least a major gonadotoxic treatment that would result in them getting fertility and becoming infertile in the first place. And so there is a possibility, and I've shown, and many other labs have shown, that those cells can exist within this cortical tissue that we save. And so a big motivating driver of the research that I do is the need to improve restoration, either through in vitro maturation or treatment, or long-term functioning transplants in a safe way. And so the concept is quite simple conceptually, but you'll see that it becomes more and more complex. So the idea is that we would isolate out the desired cell aggregates that we want, those primordial follicles with the potential egg cells surrounded by the hormone-producing cells, and we would put it within this support structure that can then be transplanted back, and ideally without any other cancer cells. And so these are kind of the parameters that we've come up with to kind of test different scaffolding designs. And so first we took a page out of some of the regenerative medicine biology books at the time, and this was 2014, 2015, and everyone, it seemed like in the field, was using decellularization. So why not start with the exact natural scaffolds that exists within the organ? So decellularization is a washing or an enzymatic type of digest, depending on your protocol, that removes all of the cells from that organ tissue, and what is left is the extracellular matrix, fibrous proteins, and the things that make them control those physical properties. And so it's the scaffolding that exists in all of our organs that makes us three-dimensional. And so what we did was we took human cortical tissue pieces and decellularized them to remove the cells there. We also did this in a whole bovine ovary, and you can just see, I like to show this image because it's a mass amount of extracellular matrix that makes up the ovary, and we only talk about a few of those cells, and as a biologist, I find this quite interesting. But you can see that most of what remains within that organ is is extracellular matrix. And so we use these as a scaffolding or a platform to reseed cells onto and use as a transplant. And so we did this in mice. And so you can see the decellularized scaffolding here. This is with kind of a lowish mag scanning electron microscopy. You can see the primary cells that were isolated from murine ovaries. And you can see here in some of these false-colored SEM images that the granulosa cells really did like this material and even started forming some of these follicle-like shapes within the matrix. And so we put in this transplant into an ovaryectomized mouse. So the ovaries were removed from this mouse, and we put this underneath the kidney capsule. And what it did really well was it increased their serum estradiol levels, and we were able to initiate puberty in these adolescent mice by using these transplants because it produced all of those hormone levels. And I'm showing you here some follicles that reformed within the matrix that we seeded, but really honestly, it was not at the efficiency that we were hoping for. And so while the ones that stayed aggregated, the oocytes surrounded by those granulosa cells, it worked well, this happened at a very low rate. And so what we wanted to do was use 3D printing technology to establish our own scaffold design in a way that we could seed more follicles. And I'm showing you a video of our printer here with the Pats logo because they're playing tonight, and I'm from Massachusetts, so go Pats. Don't want to ostracize too many people because I know they're playing the Giants. But anyway, so this is our 3D printer, and we wanted to create our own kind of porous structure. And so this is kind of what it looks like from the top-down view of several layers of struts, and it's just repeating all the way through. So, I mean, the first few designs that we tried, I think were kind of obvious. It's a round follicle. We made round pores. That didn't work well at all. But the ones that we down selected are here, and this is 30, 60, and 90 degree advancing angles. And then this is a Z-depth analysis of what our follicles that we initially seeded on would feel. And so this is a 200 micron depth, and you can see that there's pore attachment points available at both the 30 and the 60, but not in the 90 degree scaffolding design with the 200 micron depth. So this is, again, the centralized oocyte and a few granulosa cell layers. And so obviously they really liked the ones with the strut that overlapped underneath, and you can see that these pore structures were able to maintain the oocyte in the center, the basal membrane of the main follicle, and then expansion throughout the pore. And this is shown even more so here, that the three-dimensional structure of the follicle, the spheroid, is maintained. And through optical slicing, you can see that the oocyte is in the center. And so they produce estradiol in culture over time. And once we saw that, we were able to add HCG into the media. So this is all in vitro right now. And an M2 egg was released from the follicle without any mechanical or enzymatic digestion through the pores. And so with this, we were very excited and thought that this would likely work as a transplant if we were able to get release of M2 fertilizable eggs in this way. And so for the mouse transplants, we removed both ovaries. We kept the rest of that reproductive tract intact. And mice have a nice bursal sac around their ovary, so we maintained that sac, and we replaced their native ovary with the 3D printed scaffold seeded with follicles into that same bursa. And so you can see that vessel infiltration occurred. So this is a PCAM stain for endothelial cells. You can see a corpus luteum developing here, and some of the vasculature being recruited by those growing antral follicles. And we know that that vasculature works because the peptide hormones were detectable in the serum of the mice that had the implant, opposed to the ones that had just the blank 3D printed scaffold without any cells in it. And so the next thing we did was we used GFP positive green fluorescent protein follicles in the 3D printed scaffold. And you can see just from the reflection of the fluorescing GFP that the oviduct in the mouse remains intact, and that the blood vessels are infiltrating from the mouse, but the mouse itself is not green. And the idea behind that is that we wanted to make sure that the eggs released from this mouse came from the transplant and not from any remaining cells that were within the mom. And so when we mated them, they had green fluorescent protein pups, and this is an example of this pup here that was next to one from a different litter. And so this transplant was able to restore cycling through vaginal histology. We can determine those cycles in mice. They delivered healthy pups, and this supported through the progesterone production from this transplant as well. And then those pups went on to have their own grandpups at the normal Mendelian ratios that we were expecting from those mice. Okay. So humans aren't mice. So what are the next steps? How much time do I have?
5
minutes, okay.
Yeah.
So I want to just touch on a few more points. And so there's much more organization and compartmentalization in a large adult large animal than in mice. And so this is, I think, very well seen here with decellularized cortex and medulla from bovine ovaries. So these are, and the same looks similar if anyone's seen like an H&E cross-section of a human ovary. So you can see that the primordial follicles reside up here, which is the portion that we save for future transplants for our pediatric patients. And the medulla region it's much different. It has large growing follicles and vessels. There's also this great research that's come out in the last few years that has identified using 2-photon microscopy and the second harmonic to identify collagen fibers that exist in a much more concentrated way around primordial follicles than they do around growing follicles. And then recently, Nagamatsu's and others have shown that if you remove some of this extracellular matrix protein around primordial follicles that are meant to remain quiescent until they're activated to grow and potentially ovulate, that it releases that pressure. But that pressure can actually be restored by adding back physical pressure within the culture system. And so we know it's not just biochemical cues, but it's actual physical forces that control primordial follicle activation. And so this is some of the research that we're doing in my lab is looking at viscoelastic properties. So again, those physical pressures of the ovary compartments. This is using atomic force microscopy and nanoindentation microscope that basically touches the tissue. And this is a bovine ovary slice. And you can see that there's increased rigidity at the cortex region that drops when you get closer and closer to the inner medulla. And so I'm going to fast forward some of these, but But this is all to say that we're investigating the extracellular matrix composition and the physical properties of human ovaries, but we started with porcine ovaries to kind of establish this as a proof of concept, to develop the next steps for what will our human bioprosthetic ovary scaffolding look like. And so we did this in a very regular way by slicing porcine ovaries in 2 anatomical directions. So this is axial and sagittal. We decellularized all of those pieces, and we performed proteomics analysis and validated with immuno-PCR. So the idea is that we would get, in this case, a complete map of 1/8 of the whole ovary. And so we did a proteomics analysis, and we found over 1,000 proteins. 317 were significantly differentially expressed across slices. After several stringency criteria, because we want this to be a real strong foundation for our research going forward, we identified 96 matrizome proteins, about half of which are significantly differentially expressed across the depths of the ovary. And we even identified 11 matrizome proteins that have not been identified in previous ovarian protein screens. And so the idea is that we would create these heat maps and spatial quantifications and localizations of different proteins. I'm showing collagen 1A2 here. So you can see that this is the cortical region, and it's just much more highly expressed here than in the medulla region. And these are some examples of other proteins that we've identified. But I want to wrap up and just say that our next steps are to tease out what out of those matrizome proteins and what out of the physical properties actually control the quiescent nature of those primordial follicle banks and allow them to grow in a way that is appropriate. So a few per cycle and ovulate one at a time. And to regulate this within a scaffold that is really the ideal kind of transplant for a long-term function. And so I hope that that's what you kind of took away from my presentation here, and that really our goal is that this bioprosthetic ovary would restore fertility and hormone function for long term, and that we need to consider those facts. And with that, thank you very much.
Thank you. Thank you for quite an enlightening look in to the future. Any questions from the audience?
Thank you very much.
Yeah.
I enjoyed this very much. So let me just ask you on the artificial ovaries that you transplanted, where you had isolated the follicles. So you showed that they made significant more estradiol than you saw in the controls. Is that correctly understood?
That was from in vitro studies.
This was from in vitro. So where did the estradiol come from? Did you supply antigens to the culture medium?
Yes, we had FSH in the medium.
FSH, but not antigens?
No.
Then you don't make estradiol. You have to have antigen and granulosa cells to make estradiol.
So there's theca cells that form on the outside, because there are some stromal cells that come along for the ride when we do the digestion process. Yeah. Yes. Yes, there's a few cells that must transform into theca cells, because you're right, that's how we would get it. Great question.
Dr. Keefe?
Terrific talk. Have you had a chance to look at the nature of those matrizome proteins? I specifically ask about one theme. We just published a paper in Charge this month where we report for the first time that there's actually a lot of amyloid-like substance that's inside the oocyte. But the way we came across this is it turns out in yeast myocytes, there's the human anti-amyloid antibody is heavily labeling. So it turns out there's a theme that many structures use this prion-like domain that you find in amyloid to package things. And I can imagine that very tight packaging of extracellular matrix around the primordial follicle. It would be a perfect theme, structurally, to have prion-like domains where they're really tightly folded and they have their own interactions. It would be interesting to look to see, as you explore the, what are the common themes, whether there's any prion-like domain proteins that are in those
I think I'm
structures.
missing a key word. What types of?
Prion, like P-R-I-O-N.
Yes.
Yeah.
Yeah.
As you know, prions
Right.
they have their own lifestyle, but that same motif is incorporated in many proteins, especially where they have to package rather tightly and securely. And it would be, a perfect way if you were to design like a primordial follicle with extracellular matrix binding it tightly to see this prion-like domain. And it has implications for aging. I know your group, Duncan and some of the others, have looked at aging, and because as you know, these amyloid-like substances have a tendency to degrade over time, and so it would be a way to link a pathophysiological process, aging, with a proteomic question. So
Yeah.
just a thought, yeah.
That's something to look into. Thank you.
I want to ask you more of a clinical question. So what is the vision? Where are we going with this? Specifically, what is the advantage of this amazing 3D model compared to the ovary where tissue gets transplanted? And is it going to be specific to which patients we're dealing with in terms of like patients who don't have ovaries, et cetera? And are we looking at an in vitro or in vivo egg growth?
Great question. So I think like anything with assisted reproductive technologies, the most natural point could be better, or those that are already established technologies within the clinic. But I see a few patient populations that this could really help. Those that have a high chance of having cancer cells within their ovarian tissue, they didn't have another option to bank any potential gametes. The other ones maybe some of the POI patients where there's the microenvironmental changes that we could change. I foresee this both hopefully being used in vitro and as a transplant. I hope to establish a different type of transplant that takes out fertility and separates out fertility with hormone function, and so they restore those hormones in a different way, but could then use an in vitro system for fertility.
Sounds good. Okay. Thank you very much. It was a great presentation.